Good afternoon, my friends. We're going to be working with simple machines today and work. Let's get after it because I'm going to try and keep this under 12 minutes. So today we're talking about simple machines. We're going to talk about ramps, pulleys, levers, and gears. On a ramp, we have two options. We can either, change this over to red, we can either lift an object straight from the ground, straight up and put it on a platform, or we can use a ramp. Now in this case, I put a little cart, little wheels on my ramp to reduce friction. And what we found in the lab is that this option with the ramp takes less force, but a bigger distance. So we're going to pull this whole distance. This one took a great deal of force, much more force to just lift it straight up, but it took a smaller distance. And when we looked closely at this, we found that this work is roughly equal to that work. Now we're going to call this the input work because that's what you're putting in when you use a ramp. And this is your output work because this is basically what the ramp did for you. It lifted the object up here for you. So we're going to call this side output. And we'll say that the work input is equal to the output work, and that's roughly equal. Now if we looked closely, we would find that this force is really a little bit more than it should have been because there's some friction here as you pull it up. So if it was supposed to have been like 5 newtons, it's really like 5.3 newtons because of this small amount of friction here. And of course, friction converts energy into heat. So really, your work input is equal to your work output plus the little bit of heat due to friction. Right? So we can write this. That's our big idea here. Work input equals work output plus heat. Now when there's low friction, there's low heat. And we can ignore this part and say that the work in equals the work out. Now the rationale for this is pretty cool. If we look at our change in potential energy here, we went from an object having no potential energy to up here having some potential energy. And no matter how I got there, its potential energy once it's here is the same. So the potential energy has to equal the work done on the object, which is the same whether you do the work this way or this way, because you're giving it the same potential energy in the end, and that energy, of course, comes from you. All right, so far so good. Now, one other thing we noticed is that if this distance, if the ramp, so let's write this down, if ramp is 5 times longer than this distance, this height, and I'll label the height here, boom, boom, then this height, okay, the force input, that's this force, is 5 times smaller. That should be an H, sorry. Awesome. So that just tells us, hey, if it needs to be equal, if this guy is 5 times bigger, then this one has to be 5 times smaller. That's just the way that works out. Awesome. I'll switch over to a new color and we'll talk about pulleys real quick. So let's say we're using support strands. We're using 4 support strands. So 1, 2, 3, 4 support strands. And this rope goes over the top and comes out this way. And that's what I'm going to pull that way on. Right? And I'm trying to lift this thing, and let's say that this thing is 100 newtons. It weighs 100 newtons. Right? Over here, we're going to call this the input side. And over here, of course, this is the output side. So you're putting in work here, and you're getting out work over here. And we found in this case that this is a small force, but a big distance. And over here, we lifted something really heavy. It was a much bigger force than what we put in, but we only lifted it a shorter. We only went a shorter distance. Now what that means is for the distance side, if this is 2 meters in between here, that means in order to lift this guy up 2 meters, I've got to pull out this chunk of 2 meter rope, this 2 meters of rope, this 2 meters, and this 2 meters for a total of 4 times 2, 8 meters of rope. So my distance of pull here is 8 meters, and the distance I get out of that is only 2 meters up. I'm only lifting this 2 meters. Now, if the distance is 4 times bigger, we just said the force is 4 times smaller. We know to lift it, we've got to have a force of 100 newtons. And over here, my force is going to be 4 times smaller, so it's going to be 25 newtons here. Now this together is 200 joules of work. 200 joules over here. This is equal to 200 joules. So we can see that the work in is equal to the work out. If there's no friction, if there is friction, so this is no friction. If there is friction, the work in is going to have to be greater. This force won't be 25 newtons, it'll be more like 35 newtons to make up for all the friction. So your work in is work out plus heat. So the difference between these two is going to be heat. Yeah. So say if this was 30 newtons, then 30 times 8 would be 240 joules. And I'm only supposed to use 200 joules, so 40 joules must have been converted to thermal energy to heat by friction. All right, awesome. That's pulleys. Let's go to levers. Now, if I were to lift this lever, let me switch over to a new color real quick. I'll go to green, I guess. And I were to lift this thing up to here, right? My bar is like this. This side, the side we're lifting on, so this is the input, this is the output. And we can see here that this object, there's a distance it moves, there's a distance I move. This is a small distance. This is a big distance, right? So that means that this force must be small, this has to be light, and that means this has to be big. That means I'm going to push really hard and only lift something really light. I'm going to lose force in the interim. Then the question is, why would I do that? Why would I want to lose force here? And the answer is, hey, I move at a big distance. So if there's something that I value distance over force, so I want to move something far but not heavy, I'm going to use this route, right? So this is moving light objects a long distance. If I wanted to do that, I would use this kind of lever. Now let's look at this kind of lever. So I'm going to switch colors one more time so we can see it. I'll go to blue on this one. And if I do the same thing, I lift it up to where it's level. It doesn't matter, it doesn't have to be level. I'm just choosing that for convenience. And we can see there's that distance here, and there's the distance. Again, this is the in, this is the out. Now in this case, my distance on the in is big, and my distance on the out is small. That means my force in is small, and the force out is big. So this allows me to lift heavy things a small distance. Again here, the work is equal minus whatever heat is generated. So if friction is small, the work in is equal to work out. If friction isn't negligible, then the work in is going to be greater than the work out, and the difference between those two is heat. All right, gears. So let's say we have two discs like this, and they're attached together so that when one rotates, the other rotates. You can see that as the big disc rotates one turn, the little disc rotates one turn, and the little disc rotates a smaller distance around than the big one does. So if we attach a rope and wind it around the big one and wind a separate rope around the small one, and let's say we attach that rope down here to a heavy weight, and we attach this rope to a spring scale. This is the one we're going to pull on. This is our in, this is our out. We can see here that when one rotation, this is going to move a big distance. So it's going to be a big pull, and this one's going to be a smaller distance, so a small distance, which means this is a small force and a big force. Set up in this way, we're going to be able to lift heavy stuff, but we're going to have to pull really far to get to go a small distance here. Right? Now if we reverse this and we put, let's draw it real fast. Notice that's the exact same thing. This always works. This force distance thing always works this way. So if we instead drop this down and we say, okay, we're going to put the weight coming off the big one now. We're going to lift with the big one. That's going to be our output. And we're going to pull the rope on the small one. That's going to be our input. Notice here that the distance is small. This distance is going to be big. Force must be big. Force must be small. So this is one of the times when we'd be lifting something light, but a really big distance. And we'd be getting that extra distance of pull by saying, hey, you know what? I'm going to put a bunch more force into it. All right, now I'm going to talk about mechanical advantage. So the mechanical advantage tells you how much force or distance you'll get out of a machine, depending on whether you're using a machine that gets extra force or extra distance. There are two ways to calculate mechanical advantage. So MA is equal to either the force output, so the force done by the machine, divided by the force input, or mechanical advantage can be calculated by saying the distance input, so how far you pull, divided by the distance output, how far the machine moves the object. So those are two different ways, and if you use these two ways, they're going to give you the exact same answer, even though the inputs, outputs are reversed here. Now what that means is a mechanical advantage greater than 1 means that the output distance, if it's greater than 1, must be bigger than the input distance. So this is making you strong, right? So you're like, oh, I can pull farther. So in this case, the force output is going to be big, and the distance out is going to be small, right? Which means, of course, that the force in was small and the distance in was big. Right? So this makes you strong. So you can lift things that you normally wouldn't be able to lift. Right? So you can lift a 500-pound piano if you're using a machine with a mechanical advantage greater than 1, especially much greater than 1. Now equal to 1 means that there is no advantage. Right? So here the force out must be equal to the force in equals distance out. It's just like lifting it, except there's going to be some friction, so it's going to be a little bit harder. This would be a stupid machine to use. Less than 1 is just the opposite. So if this is less than 1, that means out must be smaller than in. So force in is greater than force out. So you're putting in more force than you're getting out. But the opposite side of that is that the distance you're getting out of the machine is greater than the distance you're putting in. So this allows you to move stuff farther than you normally could. So if you really need to move something 7 or 8 meters, but you only have a meter-long arm, well, heck, this would be a great machine to use. Now, to do this, you're going to have to be really strong because you're going to have to lift with way more force than what you're getting out of it. But you could do that 1 meter of pull and get 7 meters of lift this way because your distance out is much bigger than distance in. All right, let's do one example problem, and then we'll call it quits. So here we have Rafi, who's trying to rescue Nathan, who's fallen down a mine shaft that's 25 meters deep. And Rafi has decided to use 6 support strands, and Nathan weighs 800 newtons. So you're going to pause the video here, and then answer these the best you can. Come back, and I'll show you the answers. So let's do these first 3 together real quick, and then we'll do the last 2 on the next slide. So the mechanical advantage here is equal to the number of support strands of the pulley. So if there are 6 support strands, we know it takes it 6 times less force to lift, but we pull 6 times more distance. So our mechanical advantage here is equal to 6. How much rope will I have to pull to rescue Nathan? He has to pull 6 times more rope than the distance he lifts. So it's going to be 25 meters times 6, which is 150 meters of rope. How hard do we have to pull or lift the rope if friction is negligible? So we know that the equation work in is equal to the work out plus whatever heat is generated through friction. And because friction is negligible, we'll say, oh, that's going to be a 0. So my work in is equal to work out. And of course, the work in is equal to the force in, distance in, equal to force out, distance out. Now I know my output distance is the 25 meters. I know my output force is 800 newtons because that's how much we have to pull to lift Nathan. I know my input distance is going to be 150 meters. And I just need to find my input force. So my input force is equal to the output force, the output distance divided by the distance input. And here I end up with 800 newtons times a distance of 25 meters, all divided by 150 meters of rope I have to pull. And that ends up with 133 newtons of force. So if there's no friction, Rafi only pulls with 133 newtons instead of the full 800. So which takes more work? One support strand of 6, and the easy answer here, if there's negligible friction, then work in is equal to the work out. It might take a lot more force with one support strand, but you pull 1/6 the distance. Whereas with 6, it takes 1/6 the force, but 6 times the distance. So they balance out. Now, in reality, there's going to be some friction here in these pulleys. So really, there's going to be some plus heat here. So your input force, work in, is greater than work out with friction. Some of your work is going to be wasted generating heat inside the pulleys. Awesome. So I expect you to be able to answer both ways, right? With friction and without friction. So without friction, work in is equal to work out, and that's without friction. And work in is greater than work out with friction. So you should be able to answer both ways. Now, if he goes 178 newtons of pull, how much of Rafi's work is wasted as heat? So his actual work in is equal to 178 newtons times that distance he has to pull is still 150 meters. He can't make the rope shorter. So his actual work he does is 178 times 150. And that's 26,700 joules of actual work. Now the output work is what the pulleys do, and they're lifting 800 Newton Nathan, 25 meters, and the output work then is 800 times 25 is just 20,000 joules of work. So here you can see that you're doing an extra 6,700 joules. So when I subtract these two, I find that 6,700 joules of heat was generated. That's where your extra energy went. All right, awesome. That's the end of it. Have a great day, my friends.